use the pointer, I guess. Okay, so can you hear me? Okay. My name is Akaxia Cruz. I'm impressed that you said it the right way. I'm a National Science Foundation Graduate Research Fellow in the Department of Physics at the University of Washington. I would like to thank the organizers, of course, for having me here today, as well as my collaborators, Allison Brooks, Andrew Ponson, my advisor Tom Quinn, Michael Tremmel, and Marta Voluntari. So I guess I'll have to go here. So I'm going to be talking about how supermassive black holes are affected by self-interacting dark matter, which is something that I've been thinking about a lot recently. And to sort of set the stage, first I want to do a little bit of history and literature review. So somebody has already discussed this earlier in the conference, so I'm not going to talk about it in too much detail. But the core cusp problem was something that plagued small scales for a long time. So on the y-axis, we have the dark matter density, and on the x-axis, we have the radius from the center of galaxies. And what observations see are these chord profiles on dwarf-sized scales. But dark matter only, cold dark matter only simulations actually produce these NFW or cuspy profiles. So this was a problem for a long time. And there was a paper in 1993 that briefly discussed this, that if these dwarf galaxies did in fact have large cores, that it may be due to some kind of different dark matter other than cold dark matter, or it may be due to baryonic physics. So then this was further investigated in 2014, 2015 by Andrew Ponson, Fabio Governado, and Alex Fry. And what they found was that supernova feedback also flattens dark matter cusps. So this largely erased the signature for SIDM in the dwarf-sized scales. So other problems were addressed by Allison Brooks and collaborators in 2014. So the point that I was just trying to make there was that, as I said before, baryonic physics sort of erases observable signatures of SIDM. So I want to look in a different area to try to find new signatures for self-interacting dark matter. And namely, I am hoping to use supermassive black holes to find new observable SIDM signatures. The reason why I want to do this is for a few reasons. Firstly, we have a very different mass range. So before we were looking at dwarfs, and now I want to go towards clusters eventually is where I want to end up. And so for supermassive black holes, you can kind of visualize how different these scales are, in that the dwarfs are themselves the size of the black holes that I'm going to be using to probe self-interacting dark matter. Furthermore, the redshift is quite different, so black hole activity sort of peaks before z equals 2, whereas dwarfs can be seen down to around z equals 0.1. And furthermore, it's timely. So Ray kind of discussed already the black hole dynamics that Michael Tremmel has implemented into Chenga. And you can see his papers here where that black hole physics is used, and also JWST. So two big questions. Our potential observable signatures would be, does SIDM change the AGN main sequence? So the efficiency that galaxies are creating stars compared to the efficiency that the AGN is growing. And furthermore, for projects like LISA that were discussed earlier on by a number of members in the earlier session on black holes, black hole merger rates. So the idea is sort of simple. So this has also kind of been discussed earlier in the conference, is this idea of breaking the simulation. So I want to sort of break supermassive black hole growths in that I want to sort of change what it looks like compared to what we see in the real universe, and look at particularly at high redshift. And how I want to break it is by increasing an SIDM cross-section until I'm sort of erasing properties, and then I know for sure that that dark matter is ruled out, or dark matter with those cross-sections are ruled out. And of course, this will be in a parameter space that is already limited by observations at cluster and dwarf scales. And so then the question becomes sort of how do cores affect accretion and black hole merger rates? Because the self-interacting dark matter does create cores, whereas you have more cuspy profiles due to a cold dark matter. So the way that I'm going to do it is I'm going to use Chenga. So Peter Parker over here, as we've discussed before, implemented black holes into Chenga. And of course, here's my lovely advisor in front of some tipsy initial conditions. And he has worked hard on Chenga for some time now. And so the way that I feel about using Chenga is kind of akin to a Tom emoji, which I'm going to say is similar to like a clap emoji, but its interpretation is still up for debate. So further motivation comes from this paper by DeCentio in 2017. And what she did was she simulated a volume with 8 megaparsec sides, Planck cosmology, dark matter and gas mass resolution on the order of 10 to the 5, and force spleen softening length of 350 parsecs, and of course Bellavarian Trumel black hole formation that has already been discussed in detail by Ray. And what she sees is because of lower dynamical friction in the presence of a core, you actually see these black holes taking longer to fall into, let me back up a little bit. So on the y-axis, we have the distance of black holes from the center of their host galaxy. And like I said before, in the SIDM case, you have lower dynamical friction because the dynamical friction depends on the local density profile, proportional to the local density profile. And in the SIDM cosmology, you have these chord profiles. And so you have lower dynamical friction. So the mergers kind of stall. They're kind of stalling outside of their host halo so that they never really reach the center. Whereas in the CDM case, they're always sort of sitting at near the center of the galaxy. And I know that I've seen some other work by Colin who shows something similar to this, where he looked at the distance of black holes from the center of the galaxies. And I think that the furthest that they go out is maybe half of a kiloparsec. So we're seeing up to about 10 kiloparsecs here. And so this could eventually affect the growth of the black hole, which I have seen in these very preliminary results in a simulation that I ran of Milky Way-sized galaxy. So this was a zoom run of a Milky Way galaxy, and I ran it in 3 different cosmologies. So one with cold dark matter, one with self-interacting dark matter with a cross-section of 1 centimeter squared per gram, and one with a cross-section of 10 centimeters squared per gram. And you sort of have a number of effects happening here. So mergers could be different, which would then influence the black hole mass as a function of time, as Colin discussed before, and also accretion, which I have looked at extensively. But the key takeaway here is that because the black hole is sort of sitting off center from its host center, it's not able to maybe accrete mass fast enough, or maybe because you have these chord profiles, when the black holes go to merge with each other, they're having a harder time finding each other. So that would decrease their merger rate as well. Okay, so where I'm going is, again, so we've seen this figure before. So I have actually run the Romulus C cluster, Virgo-sized cluster, akin to Michael's cluster with cold dark matter with self-interacting dark matter, and I'm currently sitting at z equals 1 and going every day. So that is to come. And so just a little bit of conclusions and future work. So what I sort of hope that I showed you today is that self-interacting dark matter does affect black hole dynamics and growth at intermediate mass scales. And what I want to do in the future is probe SIDM versus CDM cosmologies using these Virgo-sized clusters. And maybe if the growth is inhibited enough, maybe we'll have an even bigger problem with quasars in the early universe, like Daniel discussed in his talk in the last section. That's all. Thank you.
Thank you. So do you have questions? Yeah. You have a comment? A question? Good.
Yes, really nice simulations, by the way. I did have a question regarding core formation, though, in these clusters, because Davide Martisi, Roman Tessier, and I'm sure many others before him have shown that AGN feedback can actually also make cores inside of the clusters. So how can you break the degeneracy between the cores driven by feedback, which we know very little about, and the self-interacting dark matter?
Yeah, that is a really good question and something that I also worry about. So my understanding of this is that the AGN feedback is maybe not as effective as the supernova feedback at smaller scales. And so maybe because it's not as effective, we will still be able to see self-interacting dark matter signatures for a reasonable cross-section. But we'll see.
Hi. So one thing, I don't know if you've checked this, but does the change in the merger rate significantly affect, say, gravitational wave signals?
I have not checked that, but it is definitely something that I'm hoping to do in the future.
Let's thank Akaxia again.